we have our ST-Link V2 over here, and this is the STM32 plugging it. Mm, you can see this is the Cube integrated development environment. This is my non-blocking blinking function. Okay, so it's running. You can see the static variable changing, and also it's blinking. So as you can see, the this program this program is currently suspended. I will resume it to show the basic things. As you can see, the global uh, tick count is increasing at the rate of one tick per millisecond, because that is the uh, load I have set on Sysdig. You can see here, Sysdig load system code log by 1000 minus 1. By 1000 means number of ticks it produced in 1 second divided by 1000 means the load timer is the number of ticks required to reach 1 millisecond. Every 1 millisecond it reaches 0. It is a down counter. I have suspended it again to show you the values in the variables. You can see this is 100 megahertz. Let me quickly show you the program. These are the standard header files. STM32 standard input main.h and Synthesis compiler. We don't really need this one, but let it be. So let us start with GPIO-C. As you can see, this is defined as a 32-bit address, which is this one. But I'm going to teach you how you can do this on your own, because my goal was to blink the LED, the default LED, that is C13. Uh, you need to download the reference manual. Let me show you the memory map. You can see here memory and bus architecture. This is the STM32F11 advanced manual. You can download it from the manufacturer website. The 2.3 memory map. Here you have a base address and the um, maximum range for that for the each sections. Since C13, for C13 we need to toggle with GPIO-C. We will note the base address. It is very important. GPIO-C. Important. Okay, so now we'll go to this is the memory register, which is quite useful. You will go here, and these are the offsets. As you remember the base address, you need to add this offset to reach the specific value. Our goal is to trigger the ODR register which has the offset of 14, but we are not using this one. Let me show you with the highlighter. See, this is the ODR register, which is our goal to trigger. But there is a big problem. This, uh, if you use ODR and use this operation or operation to set it, this is the 14. We need to set the this one, this 13th one. Say you use this operation. Now this step is divided into three parts. First is read. Second is modify. It will read that value store in a local register, modify that local register, and then store the value back in the RAM, uh, wherever the address is. So you see there are three steps here. Now say after first step, some interrupt service routine goes and modifies, writes M in the ODR section. But now your the value that you have read is the um, outdated one. You modify it and then you store your modified value. Here you override this M. It's like M was never written in the first place. You can see this is your typical race condition where the resolve was shared between interrupt and uh, a normal thread. That is why what we do is we have multiple options. One first option is bit set reset register, which is the most convenient one. You need to remember that 0 to 15 is you write anything, it will be um, you write anything from 0 to 15, it will register as 1. But if you in the bit set reset register, if you write anything from 16 to 32, it will be registered as 0. Okay. Uh, for example, say I have to write 0 in the 13th register corresponding to in the bit set corresponding to ODR. So we'll look at the bit set reset register, which is this one, 18. We need to write 0 in the 13th bit. So what we'll do is 13, and we need to write in this block 16 to 32. So we'll do what is add an offset of 16. What this will do, this is the bit mask. What this will do is you are writing 1 in the 13th register with offset 16, that is the 29th bit, but it will write 0 in ODR. ODR is 13th here. This was our goal. Okay, now say you need to write 1 in ODR. So what you'll do is you will not use the offset. You will simply write uh, actually here we will have plus 13 plus 6, 16, that is the offset, and 1 is what we'll be using logical shift on. Let me write it clearly. One shift, a logical shift to the place of 13 plus 16, because this offset you will only use when you have to write 0. Now say you have to write 1, in that case you simply don't use the offset, as simple as that. Now the second way, uh, first way is bit set reset register. Second is alias addressing, which is a ARM native feature, but but some don't have this alias addressing feature. Some versions. Okay. Now there are many um, other ways too, but they are uh, section specific, say control block specific. But this is peripheral to address the peripheral region. Okay, so what we take is we don't take the offset uh, 14, we take the offset 18, and we write in the 13th bit if we wanna write 1, and we write in the 29th bit if we wanna write 0 uh, in the 13th bit of ODI register. Next thing is alias addressing. I did not need to use both at the same time, but I did use because for my practice as well. Now let me show you how this works. See, here we have our peripheral section. Say the size is k. Say the size is k bits. Corresponding to this peripheral section, we have our alias section, which size is whose size is k bytes. Uh, um, no, actually, its size is k bits times 32, because see, this has bits. Okay, each bit here is transformed to a word. Word is 32 bytes, 32 bits. Okay, you can see how it works. Now that is the basic demonstration. This is your peripheral base. I will represent it as P base. This is your alias base. This is A base. Now say you need to write to a specific bit in the peripheral region. This is the that specific bit. So obviously you will have some offset. This value is the offset in bytes. I will write is that byte offset, and you will have some offset in bit. Say you wanna write to the second bit, so this is the bit offset. Now, how do you reach the same address in the alias section? You need to remember simple things. One bit in peripheral section is 32 bits in alias section, which is 4 bytes. 1 byte is equal to 32 bytes in alias section. Okay, so so what you need to do is you take the, say you wanna represent a number with byte offset capital B and bit offset small b. Uh, in the peripheral region, we will represent it as p base plus b. Now you have reached that specific register, and this is the bit. Okay, we don't really use the bit in to reach a specific register to in the representation of that address, because it is a 32-bit architecture, so 4 bytes are grouped together. So this is the register, and this is your uh, this is your bit. But in the alias section, bit is also used in to reach that specific address. If you had to write something to this bit in this register, you would simply use um, you would simply use bitwise operation, write one, shift it by b. Simply you wrote, but here what we have is you can write in any bit. It doesn't matter. You will be writing in this corresponding bit only. As you can see, this makes bit addressing a one-step process, because you can use equal to instead of this bitwise operation. So let's let's address the elephant in the room. How you reach that address? It is quite simple. Since the base doesn't matter, offset really matters. Okay, so let's say your desired address is p base plus b with offset b. This is bits, this is byte offset, and this is your base. You will go to alias base, and this byte offset you multiply by 32. As I've already shown you, 1 byte corresponds to 32 bytes, and 1 bit corresponds to 4 bytes. Uh, byte offset plus 32 plus bit offset into 4. You can see easily. Now what you have done is you have reached this point. This bit corresponds to this word in the alias region. Okay, now you can write anywhere inside this. You will be writing in this bit only. That is how it works. Or now here is simple formula in the comments. Peripheral offset, this is simply byte offset into 32. This is bit offset into 4. This is alias base region. Let me show you this in the mm, manual. Where is its system address map? This looks, yeah, this is it. See, uh, this is the peripheral section. This thing is your peripheral base. Peripheral base. Okay, and this is your alias base. You can see this whole is the alias section corresponding to peripheral region. Okay, this is the small section it corresponds to. I've already explained in detail. You can see, uh, you have seen it. Okay, so now let's move on to this. I've used volatile, so the compiler doesn't optimize it. Every time it needs to check util, it has to go to the particular address and then read it from there only. Otherwise, since the program, this main function is not modifying util directly, the compiler might optimize it thinking that nothing else is modifying, even though sysdig, this interrupt, is modifying it. Now we have a simple swap function. It takes pointer as input, stores it into static array. The swapped swapped values are stored in the array, and it returns a pointer. The array is treated as pointer when passed through arguments or functions, return value as function. Now this is simple integer trick. Here result is unsigned 32-bit, CA is unsigned 32, and -10 is signed. So what happens is, if you have see, there's an order to it. If you have uh, bigger data type and smaller data type, and there you have signed and unsigned, there could be many combinations between these, but according to ARM integer promotion rule, we first check the size of uh, mm, both involved, mm, of mm, both involved. Here we have CA and Doofus. We check the size. Clearly, CA is this is CA, which is 32 bits, and this is Doofus, which is 8 bits. So first we do integer promotion, and after integer promotion, if still there is a sign mismatch, one is unsigned, other is signed, we treat both as unsigned. But you need to be careful with the integer promotion. Since CA is unsigned, it doesn't promote itself. Here, this is 8-bit, and this promotes itself to 32 bits. But there are two types of promotion: signed promotion, unsigned promotion. Since it was originally and originally a signed number, this Rufus, so it will this will follow the signed promotion. In unsigned promotion, we have uh, say it was 4 bits earlier, but now we promoted it to 8 bits. In unsigned case, it will only add zeros, but in signed promotion, it will add ones for the extra bits we added. Since this Rufus is -10, and it will promote with extra ones uh, in the most significant side. It will have ones from this side. Okay. So what happens is now this looks something like 111 and some number. Okay. CA is 9, and but because this is signed and this is unsigned, so signed is also treated as unsigned, which makes this one positive. So this all adds up to be a big number, and is already positive. So it all adds up to be a very big number. Okay. So clearly this is true. And here Dufus is unsigned, zero is Dufus is signed, you can see, and zero is unsigned. So this is also treated as unsigned, and its value jumps to some big number. So obviously this is true as well. Here we have simple clock setup. Let me show you in the manual. This RCC, this is just a macro. Let me see. You can see its value is 4. I've already written in the comments. 4 is used to set up the second bit 0, 1, 2. 0, 1, 2, 2. This is 4. So 0, 0, 1. This will, if you write some register equal to 4, it just means that you have set up the second bit. You have turned the second bit on. Okay, let me show the clock base. We go to memory map, GPIO C. No, actually we go to RCC. This is register clock control. We go here and we want the offset for this one. High speed bus 1 enable. This is offset 30, and we want to turn on the GPIO C, which is bit number 0, 1, 2. So you can see this is we are writing 4 in the corresponding register. Writing 4 is equivalent to setting the second bit. Similarly, we clear the mode register. 3 is just 1 1 in binary, and logically shifting it 26 place means we are, and then taking complement, and then using AND operation means we are clearing the 26th and 27th bit. And now we write 1 on the 26th bit, which means overall we have written 0 1. This is the 26th bit, this is the 27th. First we clear them both to 0, then we write 1 on the 26th bit. Now we update this variable, we update using this function system core clock update. Now we load the sysdig with this value. This is the number of ticks per second divided by 1000. We get the number of ticks per millisecond minus 1 because it counts from 0. So obviously it will be 1 more. You can see its value is 100 megahertz. And here I have written some garbage value because it doesn't matter what you write. This register is write reset register, means it will reset upon writing anything. Now I've used type def enum to represent the status of LEDs. Here I have used an array to store different mm, duration for blinking. This is the last tick. It stores the last recorded global counter value. This is state used in the switch statement. We enter the loop, check the state. By default, it is set LED on. It enters this block and it delays for this many ticks. We pass the last recorded tick as argument, and after the delay has been passed, we write 1 in the alias corresponding to that specific ODR alias. Actually, this should be 0 because it is active low. So writing 0 will turn it on. And after that, LED we set state as no, the logic is correct because LED is currently on. We enter the block and we off the LED by writing, we turn it off by writing 1. Then current state is off. Next, this breaks the switch and we re-enter the while loop. Now the current state is off. So we enter the second block, use delete this much, and then we write 1 on the 29th register. This writes 0 in the ODR, 13th ODR. We update the last recorded tick, use take the return value from swap in a pointer. You can see both can share the same name temp because they are out of scope of each other. They don't see each other. We store the swap values in a array, change the state, and break. Now this is CubeMX generated code for setting up the clock. Now, let me introduce you to the perhaps the most crucial part of the loop, which is the non-blocking delay. What it does is it takes the uh, current global tick counter, say it is some big number, subtracts it with the last recorded count, and generates some value. This is your duration that has passed. We compare it with the required duration. If it's more, we return 1 and it enters the required loop. But you might be thinking, what if it overflows? Because we know that 32-bit integer, if it if all f are in the biggest possible state because it is unsigned, if we add 1, it simply overflows. What happens in that case? Let me explain you using simpler example, binary 3-bit. Let's say current global tick value is 1 and last recorded tick was 6. We know that in binary, biggest value is 7. So how do you think this should proceed? What the computer does is it changes it into 2s complement, that is radix complement. -6 is simply 110 in binary 3-bit. Okay, so to convert it into radix complement, we first the computer first converts it into diminished radix, which means flipping the bits. Now this is diminished radix 2 to the power n minus m minus 1. M is your number which you are converting to diminished radix, which is n-bit binary. Okay, this is the diminished radix. Now you add 1, which changes it into radix complement 2 to the power n minus m. This is I'm taking the general case in the right side and the specific case in the left side. Okay, now you also know that, see, let me show you. This is the unsigned representation of a 3-bit register: 0, 1, 2, 3, 4, 5, 6, 7. You take any value, let's say 1. If you add, see, this is common knowledge. If you add 2 to the power n to a n-bit binary number m, it gives m back. For example, here we have 3-bit binary number 1. We add 2 to the power n, that is 8. Let us add 1, 1. Here we add 1, 2, 3, 4, 5, 6, 7, 8. You can see how we return back to the return back to the original that we started with. Okay, so using that the same explanation and observation, we can write this as minus m. You see what happened? We started with m and ended with minus m. That is what the computer uses to subtract. Now we have minus m. You can simply add it to whatever you were trying to subtract earlier from. So 1 is simply 0, 0, 1, we simply add these both, we get 0, 1, 1, which is 3 in decimal. So you see, 1 minus 6 uh, is equal to 3. So there is a built-in overflow protection. 1, 2, 3, 4, 5, 6, 7. You have 1 and you have 6. So this is the current tick value. This is the last recorded tick. Clearly, you can see the current tick value has overflown past 0. But still, if you subtract it, it will not take this distance. Instead, it will take this distance, which is 3, 1, 2, 3. So that is how using unsigned subtraction, we we have default overflow protection. Even if the current tick goes below the last recorded tick, it will always measure the distance between them as if it were proper. I mean, the signs were proper between them. And in the else case, we have written 0, so it does not enter the loop. It moves forward, and nothing much is there. Thank you for being the audience to this small and humble project. Thank you.